For those of you who skipped the previous lesson, I'll make a quick recap. We have our input data, which is in a 1000 by 2 matrix. In non-linear algebraic terms, this refers to a two-variable problem with 1000 observations. We also have our targets. I will quickly plot the data so we see there is a strong linear relationship. Here's the 3D plot. You don't need to do that. It's just that simple linear problems are quite visual, so we can afford to plot them. If you download the notebook file, you will see the same code with comments. Feel free to inspect it in more detail. Alright, let's re-examine the linear model. Y is equal to x times w plus b. Our algorithm will try to find such values for w and b so the outputs, y, are closest to the targets. Remember, when we performed the gradient descent, we started from an arbitrary number and then proceeded. Well, we must do the same thing now. However, this is tricky. Conventionally, we don't want to start from an arbitrary number we choose. Rather, we randomly select small initial weights. We will talk about that in more detail later. For now, let's declare a variable called init_range and set it to 0.1. That will be the radius of the range we will use to initialize the weights and the biases. Our initial weights and biases will be picked randomly from the interval -0.1 to 0.1. We will generate them as we did so far, by using the random.uniform method. The size of the weights matrix is 2 by 1, as we have two variables, so there are two weights, one for each input variable and a single output. Let's declare the bias analogically. The appropriate shape is 1 by 1. So, the bias is a scalar. In machine learning, there are many biases as there are outputs. Each bias refers to an output. If you recall the example we saw earlier about apartment prices and apartment rent, it involved two biases, as there were two outputs. I'll print the weights and the biases so you see how they look like. They are small and close to 0. These are the weights, and this is the bias. Alright. Finally, we must assign a learning rate, which we denoted with eta earlier. I'll simply select a value of 0.02. I found this learning rate useful for this demonstration. For homework, you will have to play around with it so you can see how different learning rates affect the speed of optimization. So, we are all set. We have inputs, targets, and arbitrary numbers for weights and biases. What is left is to vary the weights and biases so our outputs are closest to the targets. As we know by now, the problem boils down to minimizing the loss function with respect to the weights and the biases. And because this is a regression, we'll use 1/2 the L2 norm loss function. Okay, great. Next, let's make our model learn.